Thank you very much. At the outset, let me thank NASL for this opportunity. I bring greetings from PGI MER Chandigarh. Today I am going to speak on role of machine learning in hepatology. I'll be taking you through the basics of AI and machine learning, recent advances, practical applications, and what lies in the future. So we all understand prediction models are commonly employed in hepatology to support diagnosis, therapeutics, and prognostic decisions. Often, patient characteristics and blood tests are combined to predict a risk of event, which can be in form of probabilities or scores. Typical examples we know: simplified score for AIH diagnosis and med score for predicting mortality in cirrhosis. However, it can be harmful if not applied properly. Recently published authors from Europe have suggested 9 different steps for enhancing predictive hepatology in health. So they recommended to clarify the need for model, purpose, and intended use. The quality and quantity of data should be sound along with statistical methods. The risk prediction should be given in terms of probabilities rather than scores. Performance evaluation should be done at least in 3 different domains such as discrimination, calibration, and clinical utility, and further followed by validation through internal and external sets. And finally, to publish the models for others to validate. Importantly, they demonstrated the need and critical importance of sample size, and they gave a beautiful diagram to suggest how a sample size should be calculated for any predictive model. And they emphasized on 3 different parameters such as event frequency, expected variance in the model to be captured by a predictive model, and number of parameters to be included, and they suggested how to use this to calculate a sample size. So now we understand that healthcare data includes a lot of complexities, and traditional machine learning algorithms which are good at capturing the linear associations and statistical assumptions often fail to capture in real world. So machine learning algorithms comes as a rescue which can map nonlinear associations, handle big data with multiple variables with better precision, adaptability, and ability to make complex and decisions with automations. So artificial intelligence is nothing but creating an environment where computers can mimic a human intelligence, whereas machine learning is a subset of artificial intelligence which deals with computer algorithms to make predictions without any explicit training. Deep learning is a subset of machine learning which is inspired from human neurons, where unstructured data such as images, voice, biosensors related data can be fed into input layer of neurons. The deep and the hidden layers processes that information, and the output layer gives predictions for given disease. A typical example of machine learning would include feeding the manually extracted data from images such as size, shape, and cell density to computer algorithms to predict presence or absence of disease such as HCC. Whereas in deep learning, a direct image of pathology, radiology, or unstructured voice or text can be fed into deep learning algorithms to predict presence or absence of disease. Now broadly, there are 2 types of machine learning: supervised and unsupervised. In supervised learnings, the models are trained, computer models are trained on labeled datasets, and when a new dataset is provided to the models, they predict certain categories or a numerical value. Whereas in unsupervised machine learning, based on the data characteristics and similarity in the data points, the computer algorithms tries to segregate the data points into groups or clusters. Now there are different machine learning algorithms described in the literature. I would focus mainly on the decision trees and neural network based models which are commonly employed. The decision tree based models often combined in different modalities such as bagging, boosting, and stacking to improve on the predictions. It is just how the decision trees are combined either sequentially, that is the boosting technique, or simultaneously taking features from multiple data sets and then joining them, making them a better model through random forest, which is an example of bagging technique, and neural networks which I have described previously. Often machine learning models are looked at black box models, difficult to explain which features are making importance. there has been a lot of growth in this area by describing the explanation of models through model-specific and model-agnostic techniques. Of these, most commonly employed, which you can see in the literature, is the feature importance and shapely additive explanations describing which features gives critical importance to the models. So friends, till now, what we have understood is that in any machine learning process, there are three key elements: data, algorithm, and the output. Data can be structured as in the format of Excel or unstructured such as image, voice, or sensors. Technically, it is broken down into categorical or numerical values, which computer algorithms understand. And the decision tree based models such as extreme gradient boost or random forest can assimilate that information from structured data to give a particular output, which can be in terms of categories called classification, or prediction in terms of a numerical value, which is called a regression, and or defining data set into different groups called clusters, or reducing the data sets which have larger number of predictors or say features into 2 or 3 dimensions through unsupervised learning techniques called dimension reduction. Any machine learning process has to go through a phase of its life cycle, which starts with data collection, data preparation, which takes a lot of time, and exploration through exploratory data analysis. About half of the machine learning process is passed through this, because ensuring the quality and quantity of data for any machine learning process is highly critical. Training the models, followed by its validation and generalization, and then deploying those models to see its impact and randomized controlled trials. A typical AI or ML workflow in hepatology would seem like feeding the multimodal data from images, electronic health records, biomarkers, or pathological images to deep learning algorithms to the input layer of neurons, and deep layers assimilate that information and the output layer gave predictions either at the same time, which is a diagnostic problem, or a thing which happens in future called a prognostic problem. Typically, you can see in this example that an image with a tumor is shown to the deep learning algorithm directly, which can segment that area or classify whether it can be whether it is a benign or malignant, or it can make a prediction about future event death. Whereas in deep machine learning type of algorithms, one would have to extract the features which can be through radiomics or radiomic based softwares and then fed to the computers to make predictions. Now, how to evaluate the performance of these models? One has to see the bias and the variance. Bias means if the model's output is away from the ground truth, which is there at the center, it is called highly biased model output. Whereas if the model is repeated several times and it gives you a variable result, it is called highly variable model. So during the training phase of any machine learning models, one has to minimize this bias and variance to get minimum error. So there can be two situations: overfitting, underfitting, or just right. In overfitting, the models are usually highly variable, the train accuracy is usually more, and the test accuracy is always less. Whereas in underfitting, the both train and the test accuracy of machine learning models are low. To reach this minimum error, several hyperparameters have been defined in machine learning models, and tuning them helps improve the accuracy and generalization of prediction models. Now we understand any classification problem, whether presence or absence of disease, can be broken down by the probabilities given by the model by a specific cutoff, and taking true and false positives and negatives, one can calculate sensitivity, specificity, positive and negative predictive value. In machine learning language, the sensitivity is renamed as recall and the positive predictive value is renamed as precision. And the harmonic mean of this precision and recall is called F-score, which is highly important, especially if the target variable, which is imbalanced sometimes. Accuracy is defined by total number of correct predictions by total predictions. However, it can be fallacious if the target variable has larger number of categories in one group as compared to another. And there are several techniques of weightage, resampling, and choosing these specific models to overcome such problems. Performance of unsupervised machine learning can be addressed through similarity and dissimilarity matrices, and this is beyond the scope of this lecture today. There are several use cases of AI and ML in hepatology which you will see and listen over the day. It would include use of routine clinical and laboratory data to predict fibrosis, cirrhosis related complications, utilizing radiology or pathology based images to make predictions about disease or future outcomes, utilization of multi-omics data, integration with clinical data and predicting a patient's outcome. And then there is a lot of emerging literature on NLP which I'll come, and real-time biomonitoring through biosensors such as heart rate monitoring. And this field is very rapidly evolving, especially in the cardiovascular medicine, to predict, the MI and the prediction of shock. Example which I would like to give is the study led by Professor Duseja across 14 centers in 8 countries in Go Asia Consortium, where biopsy-proven NAFLD patients were taken to predict significant fibrosis, and we could ascertain that random forest-based model was highly sensitive and with the highest negative predictive value to rule out significant fibrosis in both test cohort and the validation cohort. We could explain that model through feature importance, and we could see that it is the control of diabetes, age, AST and fasting blood sugars and ALT levels that could make an importance for making this model. We gave an alternative of safe score of less than 140 and FIB4 of less than 1.2 to exclude significant fibrosis. Another important study published in 2022, where second harmonic generation microscopy based images were defined using AI based algorithms to form a score on fibrosis, steatosis, ballooning and septal morphology. And tropifexor treatment could reduce fibrosis by assessment through AI-based algorithms as compared to NASH CRN staging, which could not detect any difference with the use of tropifexor. And beautifully, they could describe the regression and the broken septa after treatment with the use of this enhanced technology of second harmonic generation microscopy coupled with AI. Another important study published in Hepatology showed use of liver biopsy specimens to predict HVPG, and it is mainly based on the degree of fibrosis one could ascertain. Important things which are also coming up in the area of liver transplantation for fatty liver diseases and all other tumor-related hepatocellular carcinoma-based resections is the VR-based studies where virtual reality models are coupled with artificial intelligence to make lines of resection and make hepatectomies. We could demonstrate in previous studies the role of AI in ACLF to predicting mortality, and we gave web-based models to predict mortality. AI tools have also been used in proteomics to guide biomarkers of infections. We could also use AI to make clusters in meta-analysis to predict which studies are outliers. Now, LLMs are evolving very rapidly in hepatology, and these are just combination of different deep learning models. They can predict what is next in the text, and they are used for data extraction, code development, predictive modeling, decision support, and patient-provider chatbots. A typical example published recently in Nature, utilizing HCP guidelines, one could make treatment management options for a given patient, such as HCV. Another important example published in Hepatology, where they could demonstrate that a chatbot can give you an answer based on ASLD guidelines. However, there are problems with LLMs such as hallucinations, because they can lie and they can give you false text, which is called hallucinations. And there is always a problem with the privacy and data shifts, which can happen if the models are not trained appropriately on the vital literature. Friends, we are moving towards multimodal data and combination of this data through AI-based techniques to make predictions and make specialized treatment recommendation for a given patient. However, there is a lot of risk of bias as of today in these index models because of inappropriate or incomplete reporting. Therefore, there have been a lot of guidelines, especially MI claim and tripod AI guidelines which has come up. Everyone should go through that to understand how these studies are reported. While there are strengths, there are weaknesses, threats to AI, including data shifts, quality of data sets, and errors. I'd like to end with this presentation and thank my mentors in Azal and everyone for being here for patient hearing. Thank you so much.